today, we have Dr. Adam Kowalski, who's going to tell us how you can use the sun as a guide to other stars in the universe. Adam?
Hello, my name is Adam Kowalski, and I'm an assistant professor at the University of Colorado in the National Solar Observatory. Today I'm going to talk to you about the sun and other stars, and in particular I'm going to go over solar flares and how we also observe them on other stars. Now, of course, the sun is a star, but the sun is several 100,000 times closer to us than the other stars. So we understand it much better, and we see what's going on the sun in much greater detail. So I know some of the things I'm going to talk about today are going to be covered in a later series, but I'm going to give you a broad overview of the sun and other stars and how they all fit together, and come back to this idea of the habitable zone, not here but around our nearest star, and a very exciting discovery with that. So the sun is one of 100 billion stars in our galaxy alone, and it's the best studied of these stars, and probably it will always be the best understood and studied star. We observe the sun at all wavelengths of the electromagnetic spectrum, X-rays, radio waves, of course the optical light that we see, ultraviolet light, infrared, and even gamma rays. The sun's atmosphere covers a remarkable range of temperatures from about 6,000 degrees at the surface, which is the range of the atmosphere that produces the light we see. And I just want to say by surface, I don't mean a surface how we're used to on Earth, but the sun's surface actually is about 100 times less dense than the air around us. But it's so hot that it produces its own glow and radiation. So that's what we see when we go outside every day. But as you go higher in the sun's atmosphere, the gas becomes 1,000,000 times more dense, and it reaches incredible temperatures of millions of degrees. These different temperatures through the layers of the sun's atmosphere, they produce different amounts of light at each wavelength. And by measuring the amount of light at each wavelength, we form what's called a spectrum. And from this spectrum, we can measure the temperature at each layer in the atmosphere of the sun. And we can also measure how the temperature changes when interesting things happen in the sun. For example, when a solar flare occurs. In solar flares, the sun's radiation at all the wavelengths of light increase dramatically. This is the flare itself. Other stars also produce flares, and some of these other stars can produce flares that are 1,000 times more energetic than the flares on the sun. So they're pretty incredible. Some wavelengths of light that we just can't see during flares from other stars. These wavelengths are just too faint. So we rely on our knowledge of the sun to understand the temperatures and the processes that produce these wavelengths that we can't see from other stars. So this is really the solar-stellar connection. Here I show the classification of stars sorted by the temperature at the deepest layers that we can see. So for the sun, this layer is about 6,000 degrees. In the upper left are the big, hot blue stars. On the lower right are the small, cool red dwarf stars. In the upper right are the giants and supergiants, which are enormous and cool. The sun is a middle-of-the-road star, a yellow star in the center of the diagram here. The next closest star to us is called Proxima Centauri, and that's one of the small, cool red dwarf stars in the lower right here. This star, Proxima Centauri, is 200,000 times the Earth's sun distance, so it's very far away. What this means is that we receive about 1,000 trillion fewer photons of light every second from this star than from the sun. So due to how close the sun is, we can see immaculate detail on the sun. In a couple years, a new solar telescope will come online called the Daniel K. Inouye Solar Telescope. It'll be in Hawaii, and it will be able to distinguish features that are tens of miles apart from each other on the sun. So why do we need to distinguish such detail on such a large object? The answer is magnetic fields. Magnetic fields will be covered in much more detail in a later series, but I'm going to talk about them very briefly because they're important for understanding flares. The sun's magnetic fields are very complex. The sun is just not a big bright ball of glowing gas. The sun is also a big ball of magnetic fields. But they tend to concentrate into very small, very strong magnetic field regions. And you see several of these here. The strong magnetic fields are where the surface of the sun is dark in this very detailed image. They cluster into small areas, but these are still pretty large, comparable to the size of the Earth. The biggest of these regions are called sunspots. The magnetic fields hold a lot of energy. And when the magnetic fields become twisted and tangled, they want to release this energy. So all this energy gets transferred to the atmosphere of the sun and causes it to glow, and that's the flare itself. So here's a movie of a solar flare, one of my favorite movies, showing you all the complexity in a flare, all the different regions that light up. And this is what we try to understand. So in a solar flare, about 100 million atomic bombs worth of energy is released into these tiny brightenings. And that's the solar flare itself. So I want to draw an analogy on Earth. The apparent motions of the brightenings are kind of like the spreading of a forest fire on Earth. So a forest fire consists of many trees that sequentially light up and burst into flames. Whereas in a flare, magnetic field clusters or bundles sequentially light up. So we don't have such dramatic movies of flares on other stars. We can't see such detail. But other stars produce much more energetic flares. So when a flare happens on another star, what we see is just a point, like when you look up to the sky, get brighter. So here's an image of a star field, as if you were to take a camera and just take a picture of the night sky. You can see some of the stars here as black points. So it's a reverse color scaling. The brighter stars are blacker here. The image on the left, there are no flares occurring, but on the image on the right, a star produced an incredible flare. It's the star that's indicated with an arrow in this image, and during this flare, the star increased in brightness by 100 times. The sun does not do that during flares. So this was a very dramatic flare in another star that we observed. So what we can do with flares on other stars is we can obtain spectra. We can measure the amount of blue light to the amount of red light. And with this, we can measure how the temperature changes during the flare. So here's a spectrum of a famous flare on another star. This other star is a red dwarf star. We call it the mega flare because it was so huge and produced so much energy. So what we show here is the flare spectrum. And with this spectrum, we can measure the temperature of the flare. So we've measured the temperature of this flare to be about 10,000 degrees. This is really dramatic because normally the star is about 3,000 degrees. And it takes a lot of energy to cause the star to go from 3,000 to 10,000 degrees. We have a classification for flare size in the sun, and the largest flares are called X-class flares. This flare, the mega flare, would have been an X 1 million flare. So 1 million times more powerful than the largest flares in the sun. There are a lot of features in the spectrum, and encoded in each of these features is some aspect about the physics of the flare. Okay, I'm going to switch topics a little bit and talk about another phenomenon we observed from the sun, a phenomenon that we can't yet observe from other stars. So this is another example of how we use our knowledge of the sun and apply it to other stars. This phenomenon happens during large solar flares, and it's called a coronal mass ejection. When a flare happens, we also see a bunch of material ejected from the sun. This was material that was originally part of the sun's atmosphere, but then is blown off. So here's a movie of a coronal mass ejection. I'm going to now jump back to the issue of Proxima Centauri, which is the next closest star to us. It is a red dwarf star, one of the types of stars that produce the megaflare that I talked about earlier. Coronal mass ejections happen during flares on other stars. It's also a really interesting question to answer for our nearest star, Proxima Centauri. Here's an image of the southern sky. Proxima Centauri is in the southern sky, but you can't see it with your bare eyes. It's a small, cool star, and it's much fainter than what you can see, although it's the next closest star to us. So there was a very interesting, very exciting discovery about Proxima Centauri recently. Astronomers discovered an Earth mass planet in the habitable zone of Proxima Centauri. Now, the habitable zone is the distance from the star where liquid water can exist in the planet, and therefore possibly life. Proxima Centauri is a red dwarf star. It's cooler than the sun. Therefore, you have to be a lot closer to the star for the same temperature as we are now from our sun. So it turns out that the habitable zone is about 20 times closer to Proxima Centauri than the Earth is from our sun. The radiation from the flares and coronal mass ejection is 400 times larger than coronal mass ejections and flares on the Earth. So Proxima Centauri is a star that we've studied for its flares. We've observed this star with the telescope in the southern hemisphere over 3 nights, and I'm showing you data from this project of the star Proxima Centauri in the near ultraviolet. All the spikes in this data here are the flares, and the biggest flare increased the star's brightness by a factor of 5, something the sun does not do. So what you can see that the star is flaring almost all the time. And so if you were around this star and on the planet in the habitable zone, it would be a very dramatic light show. So it's an open question of whether there are coronal mass ejections associated with all of these flares. So we can't detect coronal mass ejections around other stars, at least not yet. We would like to know if there is a dramatic effect on the planet surrounding Proxima Centauri from all these flares and all the material that's blown off from the star during these flares. Hopefully we will go to our nearest star one day, and we would like to know if the planet in the habitable zone has an atmosphere like the Earth, and if we can live there, or if it's such a violent place that the flares and the coronal mass ejections have blown off the atmosphere entirely. So we use the sun to try to say something about the coronal mass ejections on other stars. And we use flares as a common thread. And the secret to the flares are the magnetic fields, which are very complex, and we need very, very high detail images of the sun to understand these magnetic fields. That's how it all relates together. Understanding the stars that these other planets are around is something we may not think to do, but these other stars can be very different from the sun. And we use common phenomenon observed in the sun and stars to try to understand the environments of these other planets around other stars.
As always, if you would like to hear more from us, please feel free to get in touch. You can find us on Twitter at @NatSolarObs. You can get us on Facebook at National Solar Observatory. And we now have an Instagram account at National Solar Observatory on Instagram.